This video will go through the deflection calculations in SLB. The material properties will be reviewed as they relate to deflection calculations, so the long-term deflection settings, the service load settings. We will then show how to display the deflections on screen, and then look at the long-term deflections, Kcs Load Combinations, the recommended Simplified Method, and the Eurocode 2 approach. Finally, we will see how we compare the three different long-term deflection results. The calculation procedure within SLB as it relates to deflection calculations is that the bending moments are calculated using the gross section of the concrete, so for all ultimate and service cases combinations. Then the reinforcement is designed to resist this ultimate bending moment, so for cases that have envelope ticked. We consider minimum reinforcement, crack control requirements, and user-defined reinforcement as applicable. Then finally we calculate the deflection for each deflection method, so instant and KCS long-term deflections, the recommended simplified method, and EC2. Going to the SLB software, the three different methods are specified in the Solve tab next to Analysis. So by default, KCS must be on, and if we hover over the top, this KCS button, really this is for all instant deflections and for long-term KCS. So by default, this will always be calculated by the software and cannot be switched off. We can then also calculate long-term deflection results via the recommended simplified method, RSM, and the Eurocode 2 approach. Before we calculate the deflections and view the results, we'll review the material properties. So under Input and Material Properties, the first thing we're interested in is the long-term deflection settings. So here we calculate the creep and shrinkage parameters to section 3 of AS 3600. Now we have two options here. So we have per slab zone and user-defined global. When we set per slab zone, the program will automatically calculate the design shrinkage strain and the design creep coefficient to section 3, automatically considering the thickness of the various slab zones that have been modeled. So if we hit cancel and quickly have a look at our slab, we have a car park slab, 250 thick slabs, typically with 450 drop panels. If we select one of the slab zones, we see here the program calculated design shrinkage strain and creep coefficient, and it should be something a bit different for the for the drop panels. So that is calculated via these various input parameters. So we need to specify the basic creep coefficient. Now be aware that this final drying basic shrinkage strain, this is not the final design shrinkage strain. This final drying basic shrinkage strain is a property of the local aggregate. So this is defined in AS 3600 section 3 on page 39 under equation 3.1.7.25. So this is the basically has different values for aggregates from Sydney and Brisbane, Melbourne, and elsewhere. We also have the option to specify the design shrinkage strain and creep coefficient variability. So the code states that we must consider there'll be a plus minus 30% change in these values, so we can specify this here. So this will just calculate the value based on these inputs and the slab thickness, and then increase or decrease it. Now if we were to switch to user-defined global, we would put in our own value for the design shrinkage strain, and then we wouldn't see the value in the properties tab. But for this example, we will keep it program calculated per slab zone. Now the next thing we'll review is the service load settings. We have a few things here that we need to set. We have service load combinations, effective second moment of area, and some additional reduction factor. So the service load combinations, these are basically pre-filled in if we use the system defaults. So if we hit cancel, go to input, load factors, these are the three service load combinations that are default within the software. Going back to material properties. service load settings. We need to specify an M sustained, so this is a long-term sustained service load, which is used for the recommended simplified method calculations only. So this is chosen as the G plus 0.4Q case. Next we have a short-term service load case of G plus 0.7Q, so this is used in the calculation of M star S. And then finally we have this G plus Q case, so M star S1. This isn't actually used in the deflection calculations, this is used for the crack control for flexure calculations, but it is set in this tab. So those calculations will be shown in the in the reinforcement video. Next we go down to our effective second moment of area. So we specify the effective second moment of area for the three different calculation methods. For the Eurocode 2 approach, again we don't need to specify anything because an input of the effective second moment of area is not needed for those calculations. If you want to see those calculations in detail, just hit this Help Deflections hyperlink and it will open up the relevant section in the manual. For the recommended simplified method, we only have one option, just the I effective as derived from Eurocode 2. So this is basically was first proposed by Bishkov, so I effective by Eurocode 2, and Bishkov is the only option for the recommended simplified method. For the KCS deflections, we've got a few different options. We've got an option for basically as specified in AS3600, so I effective via Branson's formula. The form that we use, Branson's formula, instead of having basically a cube, so m cracked over ms cubed as is defined in AS3600, we have it to the power 4. The power 3 is used when I effective is evaluated only at the midspan, while in SLB, I effective is evaluated in a number of points along the slab, therefore the power 4 has to be used. Other options that we have the simplified method, which is as per equations 8.5.3.1, 2 and 3, depending on the reinforcement ratio that's calculated by the software. We also have I effective equals I gross, so for an uncracked section, if we're interested in seeing what that is, we can do it this way. And then finally we also have the option of using the effective second moment of area as derived from the Eurocode, so I effective via EC2-Bishkov. Now, when calculating long-term deflections, it is well known that the Branson's formula has been derived to correlate well for heavily reinforced sections, so basically for essentially beams, heavily reinforced beams. However, for lightly reinforced sections such as slabs, it will overestimate the slab's capacity, so the results it will provide will be unconservative. So typically for most situations we shouldn't be using Branson's formula. If we do, we should apply an additional factor. So one crude way to account for the fact that Branson's formula overestimates a slab's capacity is to apply this additional reduction factor. So this additional reduction factor is only used in KCS calculations, and it's not the reduction factor that's specified under equation 8.5.3.1 in AS3600, so it's not the 0.6i for reinforced sections when the reinforcement ratio is less than 0.005. It's not that. It's an additional factor we put on top of that. So as we can see here, if it's 0.7, for a lightly reinforced section, it will be 0.7 times 0.6 times I gross for a lightly reinforced section, which we think that this particular slab will be. So if we're going to use I effective by Branson's, we should keep this as 0.7, the recommended value for this particular case, lightly reinforced slabs. Now again, this isn't from any code, this is just an additional reduction factor applied to the software to account for the fact that Branson's formula overestimates the capacity. Or alternatively, we could just simply use the more accurate, the better representation of I effective by Eurocode 2-Bishkov, and then not have to worry about this at all. Finally, there's one more switch, the upper limit for I effective maxed used in RSM. By default, this is switched off, so this matched the settings as per versions of the software pre-July 2017. Now we have it as basically a user option. We can toggle it on. So when it's off, basically the I effective max equals I gross regardless of the reinforcement ratio, and when it's on, we apply the limit of 0.6 times I gross for lightly reinforced sections. We'll see what effect it has on the results, but generally speaking, it will make the deflections as calculated by the recommended simplified method 20 to 25% worse than the other two methods. So for KCS, we must use it as it's a requirement of AS3600. For the Eurocode calculations, we don't need it because we don't calculate I effective, and we give the user the option of switching it on or off for RSM. And if we go to the Solve tab, we see that the long-term deflection values we want to calculate are switched on. We hit Analyze and Design and let it run through. And with the analysis complete, we hit Exit. And to view the deflection results, we go to the Results tab and go to Deflections. So having switched on the two different methods for long-term deflections, we now have a few different options from this drop-down box. So initially, let's have a look at the instant deflections. So we go to the relevant load combination we want to have a look at, and we'll just set service load combination G plus 0.7Q. So we'll switch on instant and long-term KCS. So we see the contour lines, and hitting plus equals button to make the text bigger, we see the various deflection results on screen. Now to show the additional numbers, we simply click in the working area, and the program will show the deflection result as calculated at that finite element node. So pressing Shift E to show the mesh, we can see the results at the particular nodes that we click. So escape to redraw, showing the long-term deflection results again. Clicking displays the results. Another way we can display the results is clicking, dragging and dropping and releasing, and the program will show the largest deflection in the area that we just highlighted. So again, here. And then the final way we can display deflections is using the distance tool. So making sure our snap setting is snap to corner. Let's zoom into this particular column, hit the distance tool, or we could use the shortcut D, go from column to column, and hit minus to make the text smaller. And we see the span over the deflection value, and then that value is calculated for us. So we can use this to check our various deflections. So that it should be noted the deflection limits are not checked by the software. The user has to check this manually and then adjust the slab thicknesses of the steel as needed to achieve an acceptable design. So zooming extents again, making the text bigger. So these are our instant deflections for the service load case G plus 0.7Q. Again, this shows KCS here, but this is instant and long-term KCS. Now, how we show our long-term KCS combinations, we have to navigate to the relevant defined KCS case. So let's have a look at the KCS, maybe 100%. Let's look at 50% total deflections. So Again, dragging and dropping to show the values. We see a peak value of about 26.1 millimeters. And if we go to input load factors, the KCS load factors were input for combination 6 to 15. These are the system defaults. And as we can see, the program doesn't directly calculate for KCS the long-term deflections. We crudely approximate the long-term effects of creep and shrinkage on the deflection of the slab by essentially artificially increasing this service load combination by some KCS factor. As we know, this is dependent on the ratio of compressive steel to tensile steel. So the less compressive steel as a percentage of tensile steel there is, the more the slab will deflect. So we can see for 0% compressive steel, the factors are much higher, therefore the slab will deflect more, and for 100%, the factors are lower, the slab will deflect less. Again, very important that we don't switch on envelope for these cases. We don't want to design steel for these increased load cases. So yes, in summary, the KCS long-term and incremental total, long-term total and long-term incremental deflections are basically considered a crude approximation of the long-term deflections, and we input them via the load combinations and then view them by going to deflections, instant and long-term KCS, which we've done, and then specify the relevant KCS deflection result. And then dragging and dropping, we see the values. Now the next question is, what is the correct KCS combination to look at? We will discuss that later in this video. Next, we'll have a look at the deflection results for the recommended simplified method. So if we go to long-term RSM and hit total deflections, we can see the total deflection results shown in here. So again, this is slightly bigger, so a different way of calculating the deflections, different results. And we'll look at the long-term total for the Eurocode method. So 3 different calculation methods and 3 different set of results. Now you may have noticed that when we were changing between the recommended simplified method and to Eurocode 2, the program automatically changed the service combination or the load combination to the service combination we set in the material properties. If we try to change this case to something else, we'll see a warning message that the results are not valid. So again, going back to the G+.7Q case to see the correct values, yes, it will use the service case as specified in the material properties. To view the long-term incremental deflections, so for the KCS method, so hitting escape to redraw, we simply select the appropriate incremental case. So again, we're looking at 50% deflections, KCS, and for the recommended simplified method and for Eurocode, we go via the drop-down box. Now we see for the RSM and Eurocode 2 methods, the program will automatically find a blank load case and create it will create a new load case for us. So it will get the deflection from load combination number 4, the total, and then subtract the self-weight. So this is what we're looking at here, and similarly for the Eurocode. Now it should be noted that this is slightly different to what is done in the KCS method. So if we go to input load factors, we see that for KCS between total, long-term total, long-term incremental, the AS3600 gets us to subtract a value of, well, there's a difference of 1 G between total and incremental. So G being self-weight and superimposed dead load. For our EC2 and recommended simplified method long-term incremental deflections, we simply subtract the total long-term minus the self-weight. We don't subtract the superimposed dead load. So just something to be aware of. So these deflections will be a little bit more conservative. If we want to have it comparable with KCS, we just need to basically subtract the deflection due to self-weight and superimposed dead manually. Now going back to the long-term total deflection results, we can see that for the recommended simplified method, this value is starting to get a bit higher than sort of what is acceptable. Larger magnitude of deflections. Eurocode is pretty much right on the limit, and we're not sure exactly which KCS deflection value to use. And the reason is we haven't actually looked at our reinforcement results yet. So as mentioned in the introduction, the program is using the calculated reinforcement in its deflection calculations. So again, we'll cover reinforcement in detail in a separate video, but when looking at deflections, we should be aware of what's going on with the reinforcement. So we'll just look at the X direction, and then we'll look through it in more detail in a separate video. So going to reinforcement X bottom, this is the reinforcement that is designed for the bending moment envelope, and we press inside this worst case span, we see a value in millimeters squared per meter. So this is about 467,715 bottom X, and then if we go to the top, we see some small value here needed for crack control for shrinkage and temperature effects. So we have approximately 188 millimeters on the top, and on the bottom we have 467, say. And this corresponds to approximately 40% steel. So if we were, so basically this answers our question at these finite element nodes of which KCS combination we need to use. So we're probably going to be in reality somewhere between the 25 and 50% KCS deflection. So that 26.5 value we saw, if looking at KCS deflections, will be a bit worse. But the issue with these reinforcement ratios is that basically the reinforcement ratio changes per finite element node. So here we have what, 780, 760 bottom, and 0 top. So these ones will be 0%. So looking at these KCS deflections and trying to rationalize a common reinforcement ratio starts getting to be a bit tricky. And again, we haven't even looked at the other direction, the Y direction. Now, the Eurocode and RSM methods, we don't need to put in reinforcement ratio. We're just using the reinforcement that's calculated directly. And the final thing to consider is the reinforcement that we're looking at now is basically a theoretical minimum. So the theoretical minimum required to the design code. In reality, we're probably going to be detailing this in a slightly different manner. So if we go to the top, we're probably going to be putting more than 188 millimeters squared per meter in the top, and we'll definitely have something greater than 0 in this span. So as we modify our steel, go to material properties, the design will change. Now we will cover the reinforcement design in much more detail in a separate video, but just as a demonstration to see how it affects our results, we'll just put something a bit bigger across the entire slab. So some user-defined value which will be bigger than most of the steel required across the majority of the slab. Hit OK, and we'll reanalyze, we'll remesh and reanalyze. and going back to the deflection results, we put in 100% steel, so top and bottom KCS. So we'll just look at the 100% deflections. So that is less than the 26.5 millimeters we had previously. So when it was 50%, that's obvious. The load factors are less, hence the deflections will be less. Going to the RSM method, we should see the 30 millimeters has now dropped to about 24, so this is acceptable in this area. So again, looking total long-term deflections and Eurocode, this should be even lower. So yes, basically we've just sort of put some value in for the reinforcement, but really we should be doing a more detailed reinforcement design as we would be detailing it on site. Again, that will be covered in detail in more videos. So a summary of what we looked at in this video: we saw the material properties as they related to deflections. We looked at instant deflections, how to display the deflection results on screen, and we had a look at the three different types of long-term deflection calculation methods: KCS deflections, the recommended simplified method, and the Eurocode 2 approach, and how to compare the results. So summary of the key points: I effective by Branson's formula is unconservative for lightly reinforced sections. If we're going to use Branson's formula, we may want to consider basically reducing its capacity by some additional factor. Alternatively, we can use I effective by as derived from Eurocode by Bishkoff. So the KCS method is a crude approximation of long-term effects of creep and shrinkage. This is approximated by increasing the dead and live load. And the Eurocode and RSM method directly calculate the long-term effects. Now, the recommended simplified method considers more design parameters. It's a bit more thorough than the EC2 approach, so it's up to the user to determine which of the three methods to use. Another key point: long-term incremental deflections for Eurocode and the recommended simplified method is total long-term deflections minus self-weight. However, for KCS, it is total minus self-weight minus superimposed dead. And when comparing the deflection results between the three methods, we have to look at our reinforcement results so that we pick the correct KCS combination to compare to. And finally, we need to know that the user-defined steel will influence our results. So as we refine our reinforcement design, our deflection results will change also. Reinforcement will be covered in more detail in the next video. This concludes this video. Thank you for watching.